Last week, we made a connection between simple harmonic motion and waves. We said, first of all, that waves are a means of carrying energy from one place to another. So, for instance, you're swimming in the swimming pool, somebody throws a rock in the swimming pool or does a cannonball off the diving board into the swimming pool, you feel the energy from that person or from that rock, and you do that. You feel that energy because the water wave carried the energy from one place to another. That's what waves do. There's an earthquake in the middle of the ocean. Okay, there ends up being a tsunami. Okay, sometimes on shore. Waves carry energy. There's a wind blows in the middle of the ocean, and that wave comes in and erodes the sand away from the beach. The energy of the water wave that carried the sand away from the beach came from the energy of the wind that was transferred via a wave. That's what waves do. They carry energy from one place to another. But how do they do that? And here's the connection between the two, simple harmonic motion and waves. Waves are really just the simple harmonic motion of individual particles within the wave. Now, we had two kinds of waves. First kind was called a transverse wave. If a transverse wave that looks like this was traveling to the right, then the particles undergoing simple harmonic motion were going up and down. The particles in a transverse wave vibrate perpendicular to the wave travels. In other words, moving to the right, the particles are vibrating up and down, up and down, up and down, up and down, back and forth in simple harmonic motion, perpendicular to the way the wave travels. A longitudinal wave, although it's much harder to draw, also has simple harmonic motion. If the wave is traveling to the right, then the simple harmonic motion of these waves is to the right and left. So the particles are going back and forth in their own little area like this, but this time parallel to the direction of motion of the wave. So it's simple harmonic motion in both cases. One, simple harmonic motion perpendicular to the way the wave travels. The other one, parallel to the way the wave travels. Transverse versus longitudinal waves. Let's look at those in a little bit more detail here. Here's the transverse wave. We labeled a crest for a transverse wave, which is, of course, the top of the wave, and a trough, which is the bottom of the wave. We know the particle motion is perpendicular to the wave, and we know the wavelength is the distance over which the wave repeats itself. Wavelength, lambda, from crest to crest, or we could say from trough to trough, or we could say from this position to this position. The distance over which the wave repeats itself. Now, finally, the amplitude of the wave. Here's one that's not labeled. The amplitude of the wave is the size of the wave, right? It's measured from where to where? You tell me, actually. Let's say I'm going to start right here. Laura, where's it going to be measured to? Good. It's measured from the trough to the equilibrium position. Or you could say from the equilibrium position to the top of a crest. They're going to be the same value. Okay, so the amplitude of the wave, the size of the wave. And the size of the wave, or the amplitude of the wave, is related to what? The E word. Yep. The energy of the wave, right? The bigger the amplitude, the bigger the size of the wave, the more energy it carries, right? At some level, you intuitively know that if you're out in a lake in a boat, or in the ocean in a boat, and the water waves are getting big, that starts getting scarier. Why? Because you know that those waves that are bigger carry more energy. Intuitively, you know that they carry more energy. The size of the wave, the amplitude of the wave, is related to the energy of the wave. The other kind of wave is the longitudinal wave. The wave is going to the right here. Our particles are going back and forth, left and right. Back and forth, back and forth, back and forth. That's simple harmonic motion. A compression is an area where we have higher density. So the particles of the wave are closer together, and a rarefaction is where they're further apart. They're spread apart. They're less dense. Compression and rarefaction. Let's try to label a wavelength here. It's a little bit harder on these ones. I'm going to start the wavelength right here. Okay, I want you to tell me when to stop, when I've reached an entire length of one wave. Can you tell me when to stop? Okay, I think you might have missed it here. Tell me when to stop erasing. This better go better than the last time. Tell me when to stop erasing. Sorry, Adam, I didn't hear you when you said stop it right there. That's the wavelength of one wave, the distance over which one wave repeats itself, right? It's not crest to crest. It's not trough to trough. Hey, guys, it is harder, isn't it? For whatever reason, it does seem a little bit harder to identify a wavelength for this wave than it does for this wave. But if a wavelength here can go from crest to crest or trough to trough, then a wavelength here can go from rarefaction to rarefaction or compression to compression. That's one complete wavelength. We could label another one right here. There's an infinite number of them, just like there was for transverse waves. All right? Good? Next, we talked about the speed of waves, and we said that generally a wave travels at a constant speed. It's not speeding up or slowing down unless it goes into a new material, a new medium. As long as it stays in the same material, it goes at a constant speed. Now, that means the wave itself is going at a constant speed, not the particles. The particles are going back and forth in simple harmonic motion. The wave itself goes from the middle of the ocean to the shore, not the water. Okay, if the water always went from the middle of the ocean to the shore, then the middle of the ocean would be empty and the shore would be full of this massive tsunami, right? Water doesn't go from the middle to the shore, but the wave goes from the middle to the shore. The speed of that wave is constant, which means that v is equal to d over t. Now, what's the distance over which the wave repeats itself? What's that called? The length over which the wave repeats itself. No. The lambda, the wavelength. The distance over which the wave repeats itself is the wavelength. All right, what's the time over which the wave repeats itself? How long does it take to repeat the wave? Come on now, period force. What's the time over which the wave repeats itself? Eric? The period. V is equal to lambda over t. Now, you're going to see this equation on your data sheet, not under waves, but it's there. This one's not there, but if we replace t with 1 over f, V ends up being equal to lambda over 1 over f, and if we simplify that a little bit, it becomes f times lambda. This one also appears on our data sheet. In fact, we call this the universal wave equation. We'll use that quite a bit this unit, the wave equation. All right, you had an example problem that we left you with on the Wednesday, before we went on our field trip. And along with that example problem on 409, we had 3 practice problems. Any issues with those 3 practice problems on page 409? Number 3? Any others? I was going to say, how about number 2, actually? I think number 2 is a bit of a tricky question, actually. 1's okay? Okay, let's take a look at number 2. It says a submarine sonar system sends a burst of sound with a frequency of 325 hertz. The sound wave bounces off an underwater rock face and returns to the submarine in 8.5 seconds. The wavelength of the sound is 4.71. How far away is the rock face? So what do we got here? Okay, here's the submarine. Here's the rock face. Okay, here's the bottom of the ocean. There is a sound wave of 325 hertz that goes from the submarine to the rock face and then back again. We know that that takes 8.50 seconds. We know the frequency of that wave is 325 hertz. We know the wavelength is 4.71 meters. We want to find out the displacement or the distance traveled. What do you want to do? We're going to find the wave speed. We're going to use the wave equation for that one, right? F times lambda. It's 325 hertz times 4.71 meters. And what do you get for that, Eric? 1,530 meters per second. The speed of sound in air is about 340 meters per second. So this is about 4 to 5 times the value of the speed of sound in air. How many people have watched the movie Stand By Me? Okay, in the movie Stand By Me, these boys are out on an adventure, find a body, dead body. And then they do a whole bunch of other things. Like one of the things they do is walking on this train track. They want to go through this train tunnel. They put their ear to the track. Why do they do that? Why would you put your ear to the track before you walk through a tunnel? Yeah, to feel the vibration to see if the train's coming. The vibration of the track is effectively a sound wave. It travels faster in steel than it does in air. It travels quite a bit faster in steel than it does in air. And you can see that sound travels faster in water than it does in air as well. Why? Why does it travel so much faster in water and steel than it does in air? What is it, Kai? Yeah. Sound is a longitudinal wave, and a longitudinal wave depends upon collisions of particles like this. And if particles are closer together, then it's easier for them to collide. So the sound is going to transfer faster through those more dense mediums, water or steel, whatever. Okay, that's a pretty fast speed, but that would be typical for water, 1,500 meters per second. All right, solving for d, let's say v is equal to d over t. Rearrange that. V is equal to v times t. And what do we end up getting here? V is 1530 times a time of 8.50 seconds. Now, lightning fast calculation in my head here, I'm going to say it's 13.2 kilometers or 13,200 meters. How did I get that number so fast? It's the wrong answer, by the way. My answer is not 1,320 kilometers or 13.2 kilometers. So how did I do that calculation, 1530 times 8.5, so quickly in my head when it wasn't the answer that the book gives us here? Eric? I doubled it. That's all I did. I'm good at multiplying by 2. That's it. Why did I double it? Why is the answer that I got twice the answer that the book gives? By the way, the book is correct, not us. The book is right. Why is our answer double the correct answer? Good, exactly. I calculated this distance, the distance I drew, right? There and back. What do I want, Dom? The distance there. So what do I got to do? Got to divide that by 2. You got a couple options, really. You could divide the distance by 2. What else could you have done? What else could you have done earlier on, Laura? Divide the time by 2. Good. So instead of multiplying v times 8.5, you'd multiply v times 4.25. Right? Good. That's a good question. I like to give questions like that. I'm not trying to throw a hint of her test or anything because I don't remember what questions are on your test. It's too early. I haven't looked at it in a little while. But I like questions like that. Okay, that you either have to divide by 2 or multiply by 2 because it's not just a straight, oh, do the same thing every time. You got to think about the question, whether I multiply or divide by 2 or just leave it where it is. Okay, let's see if in number 3 we have to multiply or divide by 2. It says a fisherman anchors his dinghy in a lake 250 meters from the shore. The dinghy rises and falls 8 times per minute. He finds that it takes a wait 3 minutes to reach the shore. How far apart are the wave crests? Circling some strange units there that I don't want to deal with. Minutes. What do you got? What do we got? What's given to us here? Yep. All right, the time that it takes for the wave to go from 250 meters out to the shore. That's not the period, is it? It's not the time over which the wave repeats itself. It's just the time that it takes the wave to travel this far. It's just like the time that it takes your car to travel from the parking lot of the school to 7-Eleven. It's just a time. It's going to be, 3 minutes? We're going to convert that to seconds. So we'll make it 180 seconds. Good. What else? What else we got? Tell me something else. Nick, put your hand up. You give me an answer anyways, Nick. What else do we have there? What is that frequency? Good. So we're going to say 8 cycles per minute, which we want to convert to cycles per second. So we're going to say 8 divided by 60, which should be, I think if I remember that one, it was 0.13. Anybody have that? .13333 cycles per second, or hertz. What else? Gotta have something else here, right? Hugh, what else do we got there? Yeah, it's not the wavelength, it's the distance. It's 250 meters. I'm looking for the wavelength, right? Lambda. So let's say V is equal to D over T. 250 meters divided by 180 seconds. We get 1.388 meters per second. Okay, good. We want the unrounded number because it's not a final answer, right? So we've got that speed. Now let's say V is equal to F times lambda. Lambda is equal to V over F. 1.388 divided by 0.133. And that gives us a wavelength of 10 meters. 10 point something, but rounded to 2 digits. Do we have to double that? Divided by half? Divided by 2? No, not at all. You don't just assume you got to do that. We did in the last question, but look at the question and decide. Don't just assume that you're going to have to do that. Guys, we're going to give you a few minutes to work on some questions on page 410. Not a great deal of time, but a little bit of time just to get a head start so you don't have so much for homework. Page 410, number 1 to 9, please.